in lecture 24, we're going to talk about magnifying glass. This will be important for some later discussions that we have on microscopes and telescopes. So we need to really understand how a magnifying glass works. And again, I've drawn a converging lens. This would be a biconvex lens. Right? We have two convex surfaces on both sides. The center of the radius of curvature is at the center of the lens. And I've drawn the focal points F right here. And notice that the object is closer to the lens than is the focal point. Okay? And so that makes a big difference. All right? If we move this point back to the focal point, then what we find is an image, a virtual image, which is way out at infinity. Okay? If I move it to the left, in this case, of the focal point, now I'm going to get a real image that's inverted over here. Okay? And the farther away I move the object, the farther away the image is going to be. But I want to look at this case whenever we're within the focal length of the lens, okay? Because in this case, it's going to magnify. That's what we're going to find out here, okay? So how do we consider this? Well, first ray we can draw for sure is the parallel ray. So if I draw a parallel ray, I'll do this as neatly as I can. We know that that is going to pass through the focus. So all I need to do now is get that going through the focus. There we go. Looks about right. Like so. Okay? And for the second one, I have some choices. I could draw it through the center, or I could consider a virtual ray going through this focus, right? Which would come out parallel over here. Okay? But I'm going to go with the one through the center. I think that's what I did in my notes. Yes. Yes, that's what I did in my notes. So I'm going to have a ray go through the center of this lens. And what we'll see, and remember, a ray that passes through the center does not bend. And so this just passes straight through. And you can see that these two rays are never going to cross. They're obviously diverging. Okay? So where's the image? These are never going to cross, so we're not going to get a real image, a real inverted image over here. So where is the image? Well, what we can do is we can take these rays and we can kind of back propagate them and get a virtual image, which is going to form back here somewhere. Remember, dotted lines mean virtual rays, except for this one, which I made as the optical axis. And then we have to bring this one back as well. So I line those guys up like this. And there we go. And so what we find is that the virtual image, right, is going to be right here. It's magnified, as you can see. It's bigger than the original object. And it's non-inverted, okay? So let's put in some numbers. Let's see, what do I have here? We can use some simple numbers. If we assume that the focal length F, right? Remember, F is always the lowercase. The focal point, who I always use is the uppercase. Let's set that equal to 1 centimeter, okay? And let's pick as D sub O the object distance to be 1/2 of a centimeter. So it's halfway in between the focal point, and the lens itself. From the previous lesson, we found that the magnification would be equal to the negative of the focal length divided by D sub O minus the focal length. Well, that's going to be equal to minus, focal length is 1, D sub O is 1/2 minus 1, which is equal to minus 1 over 1/2 minus 1 is minus 1/2, so we get a 1/2 down here, which is equal to plus 2, right? Because the dividing by a fraction is the same thing as multiplying by its reciprocal. So we get a magnification of 2. And my drawing looks roughly like that's the case, because I was kind of a little bit careful here, putting the focal points in the right position. So that's the magnification of it. What do you think would happen if we moved the object closer to the focus? What if instead of 1/2 centimeter, what if we did like 3/4 of a centimeter, right? What do you think is going to happen with the image? Anybody? Well, we can either draw a picture or we can plug in some numbers, right? If we moved this back, what would that do to these rays, right? The ray going to the center would be closer to this line here. The angle would decrease between here and here would decrease, right? As I go farther away, which would cause this line to be moved back like this. Whereas this ray, right, is going to be virtually the same, right? If I move this back, the parallel ray is still going to hit right here, so this ray is not going to change. What is going to change is where they cross. It's going to move the crossing back farther, which means it's going to cross at a higher point, which means the magnification is probably going to go up. But let's just try it out. Let's let d naught, let d sub 0 be equal to 3/4 of a centimeter, right? What does our magnification equation say then? Well, it's minus, still 1. This time it's 3/4 minus 4/4, right? Which is going to be minus 1/4, so that's going to be plus 4. You see? So the closer the object is to the focal point, right, the larger the magnification, okay?
Okay.
The closer it is to the lens, the smaller the magnification, okay? This is very similar to what you would see if you looked in, say, a spherical concave mirror, like what you use to, put on your eyeliner or trim your mustache, right? It's the magnifying mirrors, right? We had one up here last week when we were doing reflective optics, right? And you saw when you put your face really close to it, you kind of looked like it was the same size face, but as you moved back, right, your face got bigger, and you could see, much finer details, like on your nose or mustache or eye or whatever, right?
Yes.
Remember that?
Yes.
Yeah. And then when you got at the focal length, something weird happened. It got all strange. There was nothing you could see. It was a blur. And then as you moved back farther, you saw yourself upside down. So that's because in this case, right, you then as you move beyond the focus, now you're just creating an image over here, and that's what we talked about a couple of lectures ago. All right, so thinking about the magnifying glass, right? If I move the object closer to the focus, staying within the focal length of the lens, though, right, then it's going to get bigger and bigger and bigger. Okay?
Okay.
All right. And the image will be a virtual and non-inverted image, which means if I'm looking from over here, right, if this is my eye, right, it appears that the object is back here and bigger, right? So this is a magnifying glass. You hold your eye up to this. You obviously want to get close enough that the spread, this angle, right, the rays don't go outside your eyes. You're not going to be able to hold it from really far away. You have to kind of get close to it, right? We're not going to talk about these details too much, but you get the idea here. If you're close enough to it and you move the magnifying glass such that the object that you're looking at is pretty close to the focal point, then it's going to look really big. So you can look at ants and things like that. And this can only be done with converging lenses. Okay? We're not going to talk a lot about diverging lenses, with one exception, which we'll talk about them when we talk about different types of eyesight. When we talk about farsightedness and nearsightedness. Okay?
Okay.
All right. That's it for this one.